Okay, we are recording.
Is it recording?
Yes,
So, is the screen visible?
yes,
All right, so we can start, right?
yes. Please start.
Yeah, sure. So, welcome everyone. I'm Ashutosh Pandey. I'm a final year undergraduate student from India, and I'm an LFX mentee. I did this in collaboration with the Linux Foundation under the guidance of Eli, who was my mentor. No doubt you all know him. So, today we'll be presenting a workshop on code coverage for the GNU C Library, also known as GLibC. So, this is the work we've done over the last 3 months, and we'll start with a high level overview of what code coverage is, how code coverage works for C and C++, and then gradually move on to the problem we solved, how we solved it, and what the approach we took to solve it. So, that said, let's begin. So, first to start off, what is code coverage? So basically, code coverage is just the percentage of code that is covered by tests. Say you have a program, and your program has multiple statements, if statements, for statements, loops, conditions, and you have to write a test case to just check if your program is working correctly. You need to know if all of your code is being reached by your tests. So this is where code coverage comes into play. It just determines which parts of code have been executed through a test run and which statements have not been executed. So in general, code coverage system collects information about running program, and then it combines it with the source information, as in you get a copy of the program annotated with coverage info. We'll see an example of this, and then you get a report on the code coverage itself. So, why is this important? This is important for mainly two reasons. The first reason is to prove that the test suite is complete. The This is self-explanatory. It's just to say that the tests you have written, do they visit all the statements and branches in your program? And to prove that there isn't dead code. Suppose you might have a case where your test suite is complete, but there is still unvisited code. That is, there are some statements in your program that are never executed. So then this code is not needed, and it can cause unpredictable behavior. Such code should be removed. So to deal with that, we need code coverage. So, what is the code coverage ecosystem like for C and C++? There are several commercial closed source tools like Bullseye Coverage, FrogLogic, Coco, Testwell, CT++. Intel has their own code coverage tool. We'll be focusing on gcov, which is the free open source code coverage tool that comes inbuilt with the GCC compiler. It's used by a lot of organizations. And code coverage metrics show you a lot of different things about a program. It shows you the percentage of statements that have been covered, a percentage of functions or branches that have been covered by the program. So again, there are multiple types of coverage depending on what information you want out of a program. The first is statement coverage. This is just whether each and every single statement in your program has been executed or not. Function coverage is whether you invoked each function, whether it's main or whether it's auxiliary functions, have you invoked each function or not. Branch coverage is to cover all the branches possible. So it might be that you have an if statement or a condition that is true all the time. So then your statement coverage will show that the code has executed, like all of your code has executed, but you won't know what will happen if the if statement is false. So to make sure that all of your branches are executed, you need branch coverage. And then there is condition coverage. If you have sub expressions or some variables in a conditional statement, if you want to show that each and every condition within that decision statement has been executed, you use condition coverage. Then we come to the main topic of this presentation, which is gcov. So gcov, as I said before, it's a source code coverage analysis tool. It generates exact counts of the number of times each statement in a program has been executed. You have a lot of options in gcov, such as branch probabilities, branch counts, function summaries. You can force it to give you a coverage of all blocks, regardless of whether those blocks are unconditionally executed or not. And the statement to invoke gcov is by adding two flags to your compilation statement. It's f profile args and f test coverage. And then finally, after the program runs, you invoke the gcov keyword and it gives you a coverage report. gcov also comes with a bunch of add-ons like lcov, which is the graphical front end for gcov, and you have gcover, which is a utility where you can get a short report of everything that you ran the coverage on. If you ran it on an entire library or an entire system and you want a high level summary, you can use gcover for that. Just to make things more clear, here's a sample program that we use, and we'll run gcov on this. Then we'll walk through everything from the how the compiler deals with it to the assembly, and we'll uh, go through that. So this is a simple program. All it does is you have a for loop that goes from 1 to 10, and if for a given number I, if the number is divisible by 3, you get divisible by 3, and if it's divisible by 11, you get divisible by 11. So you might have noticed that the second statement is never executed. So this is an example of us running coverage. On the left side, you can see that I've invoked gcc with f profile acts, f test coverage, and then finally I give gcov with the b and c command. So b stands for branch probabilities, so to show us all of the branches that were taken, and then it shows that 85.71% of the lines were executed. This is because we have two lines, that is, if I mod 11 is equal to 0, then print divisible by 11. Since I never reaches that value, those two lines in particular are never executed. So on the right side, you can see on line number 25, you have four hash symbols. So that stands for the thing that this particular line has never been executed. You can also see that it tells how many times it took a particular branch, uh, how many times it took another branch, how many branches are fall through, how many times the main function has been called. So this is an example of an annotated gcov file. Then let's jump right in. So we see that when we run an ls list command, we see that two extra files are generated when we use coverage. One is the gcda file and one is the gcno file. So when you give the ftest coverage option, you get a gcno file. It contains information about the basic blocks, as in your when we give a program to gcc, it breaks it down to basic blocks that are then executed sequentially or in a pattern, and that information about how those blocks are there and how they transition to each other is stored in the gcno file. The gcda file stores arc transition counts, your value profile counts, and your summary information, basically all of the data concerned with the coverage report. So basically, this to solve the problem of code coverage not working for glibc, we first need to understand how does it work underneath it. From the sample program that we executed, we have a few questions. First of all, what exactly changes when we add f profile arcs, f test coverage as a compiler option? So is the flow of the program altered in any way? Is something else called by the compiler? And how exactly is the coverage data counted and written to the gcda files? So for this, we first execute the program, and we take a look at the symbols that the compiler has, I mean, that the compiled program has using the nm command. So first we just execute it normally. and we see that there's a main function and there's a printf. However, when we compile the same program with coverage enabled, we see that some more functions have been invoked. You see gcov init, gcov exit, gcov main, gcov merge add, and all of these extra functions have seemingly appeared out of nowhere. We didn't make any changes to our program. So this made so for finding out what's really going on, we have to drop down to assembly to figure out how things are working. So now on the left side you can see the sample program that we have, and it's color coded, as in the yellow on the right side move and jump, it corresponds to the for loop on the left side. So this is a program without coverage, and if you want to see it in action, we use a compiler visualization tool called Godbolt. So I hope you can see the compiler explorer screen right now. So this is my program on the left side, and it's for GCC 10.2 with Intel assembly syntax. So on the left side, on the right side, we have not given any compiler options. So you just have more or less your program and the assembly of it on the right side. However, the moment we add our compiler options, which are fprofilax and ftest coverage, and then we execute the program again, you can see that a whole bunch of stuff gets added. We see a gcov main get added. We see lc2. We see lpbxo. So we'll come to what all of this means exactly. And you can see that there are some counters here. Then there seem to be some checksums. So we'll match it up with what we saw exactly. And again, the dot long over here, this is a counter for the number of functions that you have. We'll come back to that. So for now, let's drop back to the presentation. So this is the assembly code before coverage, and after coverage, all of the parts in the black boxes that you see, this is what the compiler has added. You can see that there's move and add. So basically, there is some kind of a counter, gcov 0 main. And there's a racks counter. So that counter is being incremented by one. Basically the same program, same stub is called 6 times, and in the seventh one you have a large constructor at the end. So basically, what does the stub stand for? So you see that totally a total of 7 stubs or 7 uh, parts have been inserted into the program. The first 6 are easy to understand. It's just a counter, and as long as the relevant code is executed every time, this counter increases by 1. And from the stub below, we can see that what it does is it increments the counter, but what is the counter in question? So you can see that it's a long integer of 8 bytes. The size of each counter is 8 bytes, and .lpbxo is a data structure, and it's for a static array with 6 long integer elements. So we can see that it's a read-only data section, and after the code is executed, the value of the array records the number of times the stub code is executed and the number of times the block is executed. Now, if we go back to Godbolt and let me see, I'll just remove the last 2 lines from this if statement over here and execute it again. So you can see that the dot long here, which was 6 before, has turned to 4, because this counter is the counter that counts the number of statements. Similarly, by looking at the source code, which we'll also do, we can make out what the rest of the numbers mean. So again, now the constructor. So the last part is actually a data structure. It's a linked list, and its job is to call the gcov init function, and the gcov init function is basically where the execution of the program starts, and the calling parameter is the .lpbxo structure. So after this, so basically to visualize this more easily, what we did was GCC has an inbuilt tool called GraphViz, and it generates a control flow graph. Basically, if you want to see the compiler iterate through all the passes, you can use fdump tree all. So what this does is it gives you the whole tree dump. It gives you the output of the compiler as it goes through various iterations in Gimple, in RTL form or whatever form that you want, and then you get all of that data. So this data is helpful, but it's hard to understand because it's not visualized. So using GraphViz, we visualize this data from the CFG files, which is the control flow graph. So over here on the left, you can see that during the entry, gcov init has been called, and at the end, gcov exit has been called. Also, you can see the edge counter here. So this is again something that is taken from from the profiling tool that's inbuilt into GCC. You can see the edge counter being incremented by one. You can see the various branches. BB stands for basic block, and you can basically see how the program is iterating and moving through the different blocks. And you can see for each and every basic block, gcov main is called separately, and for each and every statement it's called separately. So this data structure has several different numbers. You can see a dot long here, then dot zero, and another dot long, and then lc2. So what do all these stand for? So for this, we need to take a look at the source code, which is inside GCC. So in GCC, inside libgcc, there's a folder called libgcov driver.c. And from here, we can, by looking at this code, gcov init, we can draw a few conclusions that gcov init calls gcov info, and this gcov info is basically our lpbxo data structure. You can see that the numbers will line up, and all of these are strung together in a linked list. So let's take a look at the data structure. So over here you have the expected version number, then you have a link to the next element in the array, then you have a timestamp, and then you have a file name, and then a merge function. If we go back and take a look at the output, you can see that it corresponds to the same thing. The first dot long here is the version number. This does not change between iterations. No matter how many times you execute the program, this number doesn't change as long as your version of GCC is unchanged. And then you have dot zero. So this contains the pointer to the next one, and this dot long here is a timestamp. And after that, you have dot lc2. So your lc2 is basically a call to your file name, which is over here. You can see that dot lc2 points to the output.gcda. So basically, by matching the output of this to the gcov data structure to gcov info, we can make up that this gcov info is in fact the .lpb structure. So now in the main GCC line, gcov.c describes how cycles are counted. Basically, how do they actually count the various cycles that your program is taking? How do they count the number of functions? How does it count the number of statements? So they use a cycle detection algorithm. Basically, all of the data is represented as a graph, as in it's like a linked list but with many inputs and many exit points. And they use Havik cycle detection algorithm to find all of the paths in a subgraph. So the function for creating the flow graphs and all are taken from profile.c. It's taken from the C profiler, which is used for profiling. The GCDO and GCNO files, how are they written? That is documented in gcov.io.h. So this was enough about how gcov works underneath. Now, in the context of this, we'll be better able to understand the problem that we solved and how we solved it. So before that, in the context of ELISA, why is it required? So functional safety standards such as ISO 26262, they require that the measurement of code coverage has to be done in order to evaluate the completeness of programs. So since GLibC is a very fundamental part of Linux, although it's not directly a part of the kernel, but a lot of important functions that the kernel needs, such as fopen, fwrite, and a lot of core libraries that it needs are defined in glibc. So basically, if you're working with a functional kernel, you will have to work with glibc. And so it follows that glibc itself has to be safe. That's why this is required. So it was very strange that GCC's counting, I mean profiling, what do you call it, tool works for everything, but it doesn't work on glibc itself. When we tried running fprofile args ftest coverage with the configure command, so configure command, it failed. So it failed for many reasons. We tried adding coverage flags as arguments to the configure command. So it turns out that there is a circular dependency between gcov instrumentation and glibc. So what happens is the instrumentation in question, it calls a function called gcov merge add, which we saw earlier. Gcov merge add calls fopen and fcross, and because all of these libraries are not there, or they are linked multiple times, our instrumentation fails. And the last reference to this problem was actually from 7 years ago. There was an article which really linked, and those people were basically concluded that there was some error that could not be solved. So this was the error that we solved, and shared libraries could not be built because of the way shared libraries are called. They're used by multiple parts of the program of glibc. It causes multiple link errors, and the static library build flow, it depended on the files generated during the shared library build. So it was kind of a circular problem. We needed the shared library files, but to build with coverage, uh, those files were needed. So this was what was causing code coverage to fail for glibc. So while working, what were the main errors that we faced in more specificity? So there were several undefined references. Some libraries like libgcov.a and libgcc were not linked for some reason, and these caused the build to fail. And when the build process went further, after we tried to hack together a solution, the shared libraries went failed because of a multiple link error. So when we disabled all the shared libraries, we found that several libraries were not covered, and this was not an optimum solution because we need several libraries like libcmodules.h and selinux and nscd that is required. And if we just disabled the shared libraries and built for coverage, we would not have coverage for all those files. And the third was inconsistency with glibc versions. So initially we were having problems with 2.31, and so we used glibc 2.32. We developed the solution for glibc 2.32, but after we finished developing the solution, it worked for the earlier versions too. So first of all, is there a way to make this build pass without any patch? This was our first challenge. We thought that is it even possible, or is it some error that cannot be fixed? So basically, if you select configure time options carefully, if you disable the right parts of the library, and after that, if you note down compiler errors and manually include the right libraries, the build can be made to pass. But as this sounds, this is a very arbitrary process. It depends on the program being built. So we have given an example below. To build this, we disabled shared libraries, and we used fprofile args ftest coverage, and then with o2 optimization. You cannot build without optimization. Then when you run make fails at some point because libgcov 8 was not found, and we have to add it manually. So you have to add the right libraries at the right point in this whole thing, and then the build passes successfully. So this is not ideal because depending on what you're building, whether you're building malloc with code coverage or something else, you're going to run into problems, and you have to basically hack and stop each time. So coming to the patch, there were three ways in which the patch could be approached that we identified. One was the patch to glibc, that is trying to fix the shared libraries. Like identifying which shared libraries were causing problems, and trying to build a version of glibc that did not depend on these shared libraries. So so the first solution was a patch to glibc itself. The second solution was a patch to gcc, as in gcc is where all of the code for gcov is stored. So by changing the way code coverage worked, we could get around the problem. And the third solution was to just add a alternate configure option to glibc, which is eventually the path we took. So why did we add a configure option for coverage? We did this for a few reasons. One is because this solution was self-contained. A configure option would be an optional add-on. It would not affect the rest of glibc, and we wouldn't have to worry about running regression tests on glibc code, whether our code was causing some other side effects or not. And secondly, it's optional. Not everyone needs shared libraries, so it would be preferable if the people who wanted shared libraries could have it built that way, and the people who wanted normal glibc could just run the configure command as usual. And the solution is compact. Basically, the solution itself turned out to be very short, just around 30-40 lines of code. We made a change to the build process and how files are linked in the make config file in configure.ac and configure, and we made coverage work. And the last reason is that it fails early. Rather than you running coverage and getting some obscure compiler error, with this, right when you run the configure command, your code coverage will fail if it's not right. So it fails early, and then you can get to fixing it if it needs to be fixed. So, which files did we need to change to accomplish this? We had to change make config. In make config, we provided the information about the libraries that had to be linked at the link time. Configure.ac, so basically glibc uses the GNU auto tool system. That is, they have a configure file, and they use autoconf to configure that configure file. So we have to add the configure option there. Configure itself to check for shared libraries during configure time and display messages if the configuration process changed. And the last was obviously the documentation in install, in the text info manual, and in the news section. So just going through quickly over what changes we made. In make config, we linked the lgcov, and we linked two libraries. We linked libgcc and libgcov.a, and we made it as a conditional statement. That is, if the build gcov parameter is yes, if it's true, if it's given as a configure option, only then these options should be linked. In configure.ac, in autoconf, AC arg enable stands for autoconf argument enable. So basically, using this statement, uh, you can enable certain options, you can define certain options, and the help string displays the message that uh, should be displayed in case somebody uses the help command. So we build with instrumentation for code coverage, and by default it is no. That's why you have gcov is equal to no in the fifth line. It is only enabled when we give it a yes. And in config.make.in, we give build gcov, and we link it to the variable. So in the configure script, around line 686, there is a large array. That array includes every single variable that that gcov needs, and that the glibc build system needs. So over there we add a variable called gcov, and on line 770 we add an option to enable gcov, and on line 3380 we finally check whether the option was given. If the option was given, then we redirect it to the make config file, or else we don't do anything. And then finally there's the documentation that we included with the patch. So if you don't want to use f profile args f test coverage, you can use dash dash coverage, but it fails with configure. So what solution we got around the shared libraries was because the coverage was not working for shared libraries and it needed certain shared libraries to be built. We first built gcov normal we first built glibc normally with all the shared libraries, and after that we do another pass uh, with our uh, with our patch, and then we get all of the shared libraries. So the final configure command is just dash dash configure, disable all the shared libraries, enable our flag, which is enable gcov without se linux, disable nscd, and then your path to the installation directory. It builds glibc with code coverage. So this is to build all of glibc with code coverage. If you want to build a specific application with code coverage, Eli will give a demo at the end. So the command to make is make cxx, and after this your code coverage enabled library will be built. So how do you build with coverage? First, you have to configure and build glibc normally. If you are installing an alternate glibc, you have to be very careful to install it on an alternate system root or install it with a different prefix. If you don't do this, it could cause your distribution to become unstable and crash. So we need to build it normally first so that necessary shared libraries such as libc modules are generated correctly. Then we use our configure command followed by make cxx, and then finally with install we see and all the gcno files are generated. To verify that we have all of the files, we just go a step back into the main tree and we run a find command. So this is a sample output. You can see that all of the gcno files have been successfully generated, and after this we'll come to how to set up glibc for coverage right from the steps. So this is one example of how to do it on with prefix user by using an alternate system root, and then after that installing it. So now Ellie will show you an example of how to build a test application. So Ellie, please share the screen from here.
Yeah, okay. Yeah, I'm just, oh, share screen. Okay.
Yeah.
Screen, or maybe I share this application.
Okay, I'll stop sharing. Yeah, I did that.
Yeah, please. Okay.
Yeah.
Okay, sure. Yeah, so I'll share. Okay, I'll share with you the my.
Yeah, your screen is visible. Yeah.
Okay. Okay. So we want to show how to after we have built GLibC instrumented for coverage, how we can build a small test application using malloc, for example, and show the code coverage of malloc. So I have here. I will not go through the build process. This just takes a relatively long time, but I already have uh, the glibc instrumented for coverage installed in this directory. And I have a small application called malloc test. Okay, that it doesn't do much. It just calls malloc, and then it copies a string and it prints the string. So, so the main thing what we want to show here is that when I build and run this application, and when then I can get code coverage information for the malloc function. That was our main purpose. So, in order to build this test application, of course, I cannot use the standard libc installation on my machine. I have to compile and build and link against our instrumented glibc. So the build commands, I put it in a shell file, which is this. Okay. Okay, so you see, well, first of all, just to show that we are really, I mean, doing this for real. I'm going to remove the executable and the GCDA and GCNO files. As Ashu described, GCNO is the nodes file that allows to reconstruct the all the edges and basic blocks. And GCDA is the file that contains the actual runtime information. Then the the build command. Okay, so for the build command, first of all, I have to give the system a new. I have to define a new sysroot, which is where I've installed my instrumented GLibC, which is here. And then I'm linking, okay, so I'm linking with the libraries in the shared root. Yeah, and okay, and I'm also linking at the end with my instrumented libc. And I'm also, since I'm using here GCC version 7, I'm also linking with the libgcov. That's the gcov implementation of GCC 7. So libgcov is where all these gcov file, like as you've seen before, like gcov merge add, gcov init, they are defined here. So let's run it. Okay. Okay. So I got a new malloc test from now. I got a new malloc test.gcno from now. If I run it, okay, I'm getting the expected printout, which is the word test. Now, in order to show the code coverage I got from malloc, then let me go to the location of the source files for malloc, which are in just a second. Okay, so here I have here's the source file for malloc.c. Now I'm going to run the gcov on. Okay, build gcov is where I've built where all the build artifacts are located. The GCNO file, which it needs, and the object file. Okay. Okay, so this is the GLibC output of gcov. So gcov does two things. First of all, it prints the data of what happens. For example, okay, I just wanted to skip all the. There are a lot of functions that are not executed during this test or that are not used, but some of them are. For example, you can see here sysmalloc. So it executed in some lines, and so I get this information, and in addition, I'm also getting an annotated file. Okay, let's just do LL. Okay, so it's from now, February 3 to 2:09 p.m. Okay, this is how it looks like. Let's go to a function that I know that is called during this execution, which is int malloc. Okay, just go to the actual function. Yeah. Okay, I left it open. I thought it will go directly to int malloc. So you can see that here the number 77 int malloc was called 77 times so far. For some reason, which I cannot explain right now, but each invocation of malloc results in 11 calls to int malloc. So now it's at 77. If I run my test again. Okay, so I've run the test again. I'm going to run gcov again, and let's look again at so that this generated a new annotated file, and you can see that the number here increased to 88. So Okay, so what I'm showing here is that we have an instrumented version of GLibC, or specifically for malloc, and I can use the code coverage information in order to, to prove that, um, as we said before, that if I'm qualifying glibc functions as part of the kernel, then I can use the coverage data to show the or claim the completeness of my test qualification test suite. Okay, so that's what we wanted to show. Let's see if there are if there are any questions. You're welcome to. Okay, let's see. Is there a plan to classify, qualify GCov since its report is used in further argument? Well, yes, but that's the point here. But I think the actual qualification depends on each use case. I mean, for some glibc is a very large um, software. I think it has over 1,000 functions, and not every system needs all these functions. Well, clearly for malloc, I mean, malloc is probably a function that is used by any system, and it would be very useful to have a qualification test suite for malloc. I think this question was raised yesterday, and I think that we are planning, at least Mobileye is planning to share this information, but it would be very useful to have a qualification test suite for that is backed by coverage data for common functions like pthread, malloc, mat library. Yeah, please.
Yeah, I think the question was about the tool itself, if I understood it correctly.
Classify, qualify GCov. Yeah, the tool itself. Okay, that's not a simple question. There are ways to qualify it. Well, first of all, as we said also before, GCov is part of the, or the coverage instrumentation is part of the compiler, right? GCov is, GCov is the presentation or visualization program that service that takes the GCDA files and shows them in a nice way, and also annotates these source files. So GCov here, I think, is less important. Well, it should be, but it should be, of course, qualified. The instrumentation itself, as we've shown, is part of the compiler. It's based on other compiler features like profiling. So I think it also depends on on your approach, on each vendor's approach to the qualification of glibc. One way of qualifying is maybe to compare the results with, or to build the same application with, let's say, Clang LLVM, and compare the data we get from LLVM versus to data we get from GCC. But clearly the answer to that is yes, that it has to be qualified, and this is something that would be a nice community effort.
Yeah, can I add something? Yeah, so GCov itself is defined in GCC, and it's not. I mean, it's not a particularly difficult thing to qualify, because the aforementioned circular dependency is not there if you download an alternate GCC and just try to run GCov. I mean, to test GCov's file on that. In the main GCC tree, there are 5-6 different files. One is where gcov.c, where a bulk of all the functions that GCov uses are defined. It's mainly based off profile.c. And inside libgcc, it has all of the drivers that it uses to work and all that. So totally there are about 7 or 8 files in which the whole of GCov is defined. So we can certainly run coverage over those files and check out what it shows. Yeah,
Okay.
that's it.
Okay, regarding the second question, can you please clarify if it is now possible to provide coverage to parts of glibc or to entire GLibC? So the answer is yes, we can provide coverage to the entire GLibC.
And
Okay.
to the second question, what was done to make sure that instrumentation will not affect the change the code's function? So basically, the instrumentation was added by the compiler. We did not add those stubs. They were added by GCC. So, and the programs execute normally whether or not the stubs are present. So we're pretty sure that it does not affect the code's functionality in any way, because it's already being used like that. All it does is it just adds a layer on top and collects coverage data. That's it.
For this one, can you hear me?
Yes.
Yes.
Because I posted this question, I think maybe, I mean, by analysis, you can see that, maybe the compiler can make sure something, but in the context of safety, I think analysis may not be enough. I would suggest, can we just run 2 times of test, because the coverage is measured during your test, right? So after the test and you get the coverage. So can we run the test for the first time without instrumentation? And then for the second time, with instrumentation, then we compare the results, because the requirements-based test results should be the same, right? If instrumentation will not affect the functionality. Here we have some evidence, right?
Yes.
That would be my suggestion.
Okay, that's a good approach. I mean, it shows you that the instrumentation didn't change the program, or the program still works correctly.
Yeah, because we sorry for interrupt. Because we run into some corner cases where instrumentation will affect the functionality. I can't recall what exactly the problem, but for example, some timing sensitive functions could fail because you added some more instructions there, right? Or there's some architecture specific code, such as probably exception handling or other things that could be affected. It's just some examples.
Yes, since you have to, the main function gcov main has to be called every single time, and the counter has to be incremented, and then the control returns to the program. Yes, maybe in time sensitive scenarios there could be a difference, but for that we'd have to have such a time sensitive example and try it out.
Yeah, that's why I would suggest that we compare the results of instrumented and non-instrumented code, so that we can do the analysis for the failed test cases or the discrepancies, so that we know why. Sometimes, I mean, most of the cases can be explained.
Yes, that would be a good idea.
So regarding collaboration, I think previous question here, of course, there is a lot to or many opportunities to collaborate on follow-up work on, as we said, qualification of gcov, qualification of the instrumentation, any having test suites for common functions, or like malloc that any application uses. So there is a lot of opportunity for collaboration, and maybe we can follow up during our regular meetings in one of the working groups. That would be very useful to everyone.
Actually, I think we need to probably discuss first in the technical steering committee meeting. I mean, if we need eventually a new working group for the GLibC.
Or maybe it can be done in the tool or fun and happiness group. I forgot the official name. I'm sorry.
Yes, the tool subgroup. Yes, maybe, but we need to discuss this.
Okay.
So does ELISA have a framework for like people from outside to work with them, since my mentorship is ending, but if I want to continue working on it, so I mean, is there any method for that? Anything I need to do?
Well, I think you can join ELISA. I think you already did, and join the any of the working groups, perhaps the fun and happiness group. Everybody,
Yes.
everybody's welcome.
Yeah, sure. We have another question, Ellie. I think last question. Does the coverage cover also the mathematical library part of GLibC? If so, how are the expected results obtained? So I think yes, because if I recall correctly, while we were building, we ran into a few problems where it failed on math in the math libraries, but after that we got the output. So how are the expected results obtained? As in, basically, if you run the configure command without coverage, you will not get the GCNO file or the gcov file, which is on Ellie's screen, which shows how many times a particular statement has been executed. So if a program is incorrect or if coverage is not running, the file will not be generated at all. Either the file will not be generated or you'll get a blank file with just 3 or 4 blank lines. So the fact that we got the gcov file successfully and it outlines all the functions and it has all the counts, it shows that it's working correctly.
Yeah, if I may add, getting the GCov gives you coverage. It can tell you that the test that you run covered all the paths within a function. But I think you're referring, Roberto, you're referring to a more difficult question of really how do you know that your implementation of the math library are correct, the results are correct. Okay, so I can tell, I think I can tell what Mobileye does in this regard. So Mobileye does not use the math library from the libm. We use some other libm that was verified by by group at Intel that develops this kind of libraries, and they have the expected results, and they verify the expected results. Of course, the results don't match every time, specifically on Mobileye's SoC, but at least I mean, so I mentioned yesterday AAUs, right? So one of our AAUs is the list of the precision of the results that we get in our math library, and these values have to be taken into account. So yeah, but it's not it's not a simple task to verify that the math library provides the expected results. Yes. Did I answer the question?
Yes, in fact, I was surprised about. I would have been surprised if you were using the mathematical part of GLibC, because it provides no guarantee whatsoever on the results. Whereas I have made a research comparing the various mathematical libraries, and one was the Intel Math Kernel Library, which is much better. So in the sense that it provides various degrees of accuracy. There is the HA and the LA accuracy, where you have a maximum error over the correctly rounded values. So in fact, you answered.
Yeah, Yes. Okay. So okay. Thank you. So yeah. So I assume they are the same group at Intel did this work for us. Did we manage to get this working on MIPS? Not yet, but we plan to do so. As of now, yes. As of now, we did only on x86, but Mobileye plans to get it compiled on MIPS, or otherwise, if that will prove impossible, which currently I don't see why it should, we will simply evaluate the differences between the MIPS and x86 implementation. But I hope this method will work on MIPS as well. Okay, there is another question. Does GLibC call gcov itself, like fopen, appear in the final report? No, so it's not a GLibC, it's kind of other way around. libgcov calls GLibC, right? But if I have in my malloc implementation, for example, my malloc calls at the end gcov init, which is in libgcov, and libgcov then depends back on libc, because libgcov calls fopen, fwrite. So that was one of the problems. Okay. Okay, for MIPS support, we likely have to investigate what we did with the stack protector suppression, because MIPS needs a bootstrap relocation path in the dynamic loader.
Yeah, the gcov stubs can't run without initialization on MIPS, I think. Basically, on x86, you get an executable image from the kernel, and MIPS needs bootstrap allocations.
Okay, that's interesting. Okay, we can.
I've got a completely different question. If you have to stub, or if you plan to stub out parts of GLibC because they are shown to be unreachable, don't you lose the benefit of using GLibC as a standard system component in the first place? Because what you build is no longer what other developers whose software you consume are expecting in terms of C library. And wouldn't it make more sense to use or start out with a different C library then?
Yeah, yeah. Well, any vendor can choose any C library. Well, we are not stubbing out parts of GLibC, or well, if I take the example of the math library, as I said before, we don't use the math library. We still actually use GLibC because we get that from MIPS themselves. So I think, I mean, it could be possible to use any other implementation of C library, but specifically for Mobileye, we get this support from MIPS. So we use the libc.
Okay, so you don't plan to remove the dead code before the stuff goes into production?
No, but we are qualifying. Okay, so as I said, I think yesterday, we are qualifying. We ensure that the library works correctly by using our qualification requirements and qualification kit. The use of the library is limited to the functionality that we do qualify, and we show absence of interference, possibly from dead code or code that we didn't test through the stress test. So all of that is part of the safety concept.
I see. That explains it. Thanks.
Okay. Actually, I'm hosting the meeting that starts right now, so I think I should move to
Yeah,
the other meeting.
So thank you guys. Thank you for this meeting. And yeah,
Okay.
thank you. Yeah,
Thank you, Ashu.
yeah, thank you.
I'll press on the stop recording.
Yeah, sure. And I'll join the next meeting and see you there.
Okay.
Yeah.
Yes.